Okay, this is our video. Just kick off torque and rotation for these rotational motion equations. Right now, I have pulled up the front page of our workbook. Um, on the front, we've got all our learning targets, all this equation sheet, la di da. Right now, we are going to look at this page 3, class problems on rotational motion equations. Okay, rotational motion equations. I have over on this side, I have copied over just screenshots of motion equations and rotation and torque. This is straight from the equation sheet. So I've just taken screenshots and copied those straight over. Um, Sorry, my cat just tried to bite me there. So I've copied those straight over. Um, all right. So looking at rotational motion equations, essentially what we're going to do is we're going to look at motion equations and then go to rotation. Rotation is if we imagine right, we've talked about circular motion already, but if we imagine for rotation, rotation is kind of a variation on circular motion. Circular motion is you have, right, you have like the center of the thing, and we'll label that C for center, and then we have something that starts over here, but then circular motion is about this thing moving around the center of the circle, moving around the center of the circle, as opposed to torque and rotation looks at something if the entire thing is rotating. If the entire thing is rotating. So I don't think it'll let me do this necessarily, but no, I don't think so. Maybe. No. Okay. But if the entire thing is rotating, so you can imagine like take a globe, and the globe just sits there and the whole thing rotates and the whole thing spins. That's rotation, as opposed to circular motion. You're talking about something moving around the center. Rotation is you take an entire object and you spin the object. That's the difference between rotation and circular motion. Okay, what we have to look at for these here, what we have to look at is now we get to translate things between linear motion and rotational motion. And there's a really nice kind of one-to-one translation here. So I'll make our little key over here between linear motion and rotational motion. So linear motion and rotational motion. Essentially, if we were to look at linear motion and think about, move these closer together. Think about something's position over time, right? Position is given by x, and we can have some initial position and final position. And what we really do, right, we look at this d, this displacement, where displacement is given by x final minus x initial. What we can see is if we take this over to rotational motion, our position is now given by what angle are we sitting at? So what angle, or theta, do we start at? What angle or what theta do we end at? And then if we want to look at what's the change in our angle from our final angle minus our initial angle, we will call that delta theta. So we'll call that delta theta, which is maybe more intuitive than we use for d for linear motion, but we're so used to seeing this d for displacement or for distance traveled, things like that. And now we're going to switch this over to delta theta equals theta final minus theta initial. Okay, so there's kind of our position variables. The next thing that we can do here is we can look at our velocity, right? In motion equations, we see v naught and we see v final. So if we look at these velocities, well, in rotational motion, we call this angular velocity. Basically, you can take anything from linear variables and just add the word angular to it, and it becomes a rotational variable. So angular velocity, and we use this weird, it's omega. This is lowercase omega. It's a Greek letter because I guess we ran out of English letters. So this is omega It is not W. If you say W, I'll take your paper and bonk you over the head with the paper. But we have omega initial and omega final. Those are angular velocities. So our initial angular velocity, our final angular velocity, just like initial velocity, final velocity, but these ones are linear. These ones are something rotating. Okay. Another variable that we have are position, velocity, what kind of concludes the triad, acceleration. Well, angular acceleration is given by this little guy. It looks like an A, but it's not quite. It's alpha. It's the Greek letter alpha. I also like to call this guy fishy because it looks like a fish. So we have acceleration. Linear acceleration is A. Angular acceleration is given by alpha, or also known as fishy. Okay, one last one. One last one that we have, because the last variable that we see over in our motion equations, I see time in a few places over here. I see time. Well, in rotational motion, we can't really rotate time, so it just stays as time, which is kind of nice. Okay, so time just translates straight to time. All right. So when we take a look at these, undo. When we take a look at these, I'm just going to draw a line down the middle, right? Anything in position, we use meters. We use meters for all of these. Anything in rotation, I'll finish these off first. So meters per second is velocities. Meters per second squared is acceleration. Time is in seconds. We can say time is in seconds. That's straightforward. Rotation, though, for position, angular velocity, angular time, so theta, omega, and alpha. And this is going to be a little strange, but we're going to get used to it since we use it over and over. We will do this in radians. Now, this doesn't mean that your calculator has to be in radians. I want to make sure you know that. Radians in your calculator, the only thing that's used for is sine, cosine, tangent, which we're not going to be doing. All we're doing is adding and subtracting and dividing and whatnot. So we just use these in terms of, these are in radians. So a meter is like a radian in this conversion here. So angular velocity is in radians per second. Angular acceleration is in radians per second squared. Now, I know it's weird that we use radians instead of degrees because our calculators are in degrees. So how can we use radians? Essentially, degrees comes from, I believe it was the ancient Mayans who did their math in base 60, as opposed to we do it in base 10, right? You count to 10, and then you have a 0 that goes and counts up to a 1, and then you count to 10 again, and all that kind of stuff. But the Mayans did their math in base 60. That's why we have 60 seconds in a minute, 60 minutes in an hour, all those kinds of things, 360 degrees in a circle, because that's a multiple of 60. So the ancient Mayans really, really like to do their math in 60s. We are just kind of stuck with the leftover effects of it. That's what degrees are. So that's why degrees don't work with normal math that we do, because our math is in base 10, but degrees are in base 60, so we can't really work with those. Radians, however, radians are in base 10, so we get to work with radians. I know it's weird. We're going to take a look at it. Don't you worry. We're going to do enough that it just becomes second nature to you. So don't worry about it. Just know that that is a thing that exists. One more thing before we get down to our example problems. One more thing is, if you think of the unit circle in your math classes, right? Unit circle. We start over here on the right side, right? And that's 0. And we come up here, right? That's pi over 6, over here, pi over 3, all those kinds of things. We are moving in this direction. We are moving counterclockwise. So something else for us to note, counterclockwise, and we'll use the same notation here that your math class does. Counterclockwise is positive. Counterclockwise is our positive direction anytime we're using rotation. Okay. So now that we've done this, we have our translation key. We know what variable in linear motion equals what variable in rotational motion. It is just using the same exact process that we looked at the beginning of the year, but now we have new rotational motion equations. It's exactly the same as what we had before, though, right? You have omega final equals omega naught plus alpha t. That looks just like v final equals v naught plus at. You just substitute in v and omega, a and alpha. You just substitute those in. This second one here, we have theta final and theta initial, all that kind of stuff. I'm hoping that you take theta final and theta initial and that you can take this motion equation and turn that into delta theta, right? We just subtract omega or a theta initial, subtract theta initial to the left, and we get theta final minus theta initial, which is the same as delta theta. So we get delta theta equals omega naught t plus 1/2 alpha t squared. That is what that equation turns into. But hey, guess what that one looks like? D equals v naught t plus 1/2 at squared. Looks just like it. I give you this as far as the torque and rotation with theta final and theta initial because that's how AP gives it to you. Now that we're kind of further in the year, I can start giving you things more how AP gives it to you instead of having to give you the more simplified version because now you're used to it. Now you've kind of gotten used to these physics concepts, so we can do more straight away. But I'm hoping you see this and you immediately go angular displacement would be delta theta. So we need theta final minus theta initial. Okay. So we have those two translations there between this motion equation and this motion equation. Then between this motion equation, kind of take this intermediate step through delta theta to get to this motion equation. We are missing this one on the equation sheet. Well, don't worry about that quite yet. Or as in, we're missing, what does that translate to? Don't worry about it quite yet. We will get there. So just be patient. Hang tight for a couple problems. All right, let's take a look at these, though. So let's come to our first class problem. All right, so this is page 3 of our workbook. This is where we get to apply everything that we just talked about up here. You got to know these translations. You have to know those. You have to know that x naught is theta naught. Those matter less. You have to know that d is delta theta, v naught omega naught, v final omega final, a is alpha, time just stays as time. But those are the 5 variables that we use in these motion equations. You have to know the translation between them, and you have to know what units they use. Okay, so let's take a look at these. An object rotates in a circle, starting from rest and rotating counterclockwise. Remember, what does counterclockwise mean? Counterclockwise just means positive. Okay. It spins for 3.2 seconds, picking up angular speed at a rate of 0.76 radians per second squared. What is the angular displacement after this time? All right, so remember, how did we treat motion equations at the beginning of the year? We used the guess check method. Givens, unknown, equation, substitute, solve. Let's use the same method. So what are we given? We are given, I just looked through and I used the numbers first. Okay, it spins for 3.2 seconds. Well, if we look at the unit of seconds, that tells us time. Okay, time equals 3.2 seconds. What else are we given? This number, 0.76 radians per second squared. Well, what's the only thing that's in the units of radians per second squared? Alpha. That is our angular acceleration. So its angular acceleration, or alpha, is equal to 0.76 radians per second squared. Okay, remember we need 3 givens to solve for any unknown. So we need one more. Well, Here it is, hiding, starting from rest. So starting from rest, this is just like linear motion, where that would mean initial velocity is 0. This time, however, it's rotating, so this means initial angular velocity is 0. And what units go with angular velocity? Radians per second. Okay. Then we get this unknown here. So what are we looking for? Well, here's our question. What is the angular displacement? Okay, angular displacement, delta theta equals question mark. All right, equation. So we need to find some equation that relates time, alpha, omega naught, and delta theta. So if we look at our rotational motion equations, right, we only have these two. Is there one of those that relates time, alpha, omega naught, and delta theta? Remember, delta theta is theta final minus theta initial. Well, it'll be this one right here, right? It'll be that one, because what it turns into is really delta theta equals omega naught t plus 1/2 alpha t squared. I'm hoping that you make that jump automatically in your brain to go from this straight to this. I'm hoping you can make that jump in your brain, because that's the jump that you'll have to make when it comes time for the AP test. So delta theta equals omega naught t plus 1/2 alpha t squared. All right. Substitute. I'll just plug stuff in. Okay, we're looking for delta theta equals omega naught is 0. Oh, so that means this whole term is going to go to 0 since we're multiplying it by a 0 right there. So then it just goes to 1/2 alpha t squared. So 1/2 alpha 0.76 t 3.2. That gets squared. Okay, last thing we need to do is solve. I'm going to open up my calculator here. All right. So we get then 1/2 times 0.76 times 3.2 squared. That spits out 3.89. So I'm solving delta theta equals 3.89. And what units is theta in? I'll look up here. Anything to do with theta is in units of radians. So units of radians. All right. There's our first problem. So that's part 1. Now 1A looks at what percentage of a circle did it complete? Ooh, that's a good question. Well, this is in terms of radians. But how can we go between radians and circles? Well, if we look at our unit circle right up here, look at this unit circle. One circle, how many radians is that equal to? Well, if you know your unit circle, one circle is equal to 2 pi radians. One circle is equal to 2 pi radians. Okay, so we know that's for sure. So if we want to figure out how many circle or what percentage of a circle this is, we need to take what it made, 3.89 radians, divided by what's a full circle out of 2 pi radians. And then how do we get percentage times 100? Okay, so this should give us what percentage it is out of a circle. So 3.89 radians out of a total possible of 2 pi. Remember when you plug into your calculator, if you do out of 2 pi, what it's really doing is divided by 2 times pi. So you have to go back, and you can do it one of two ways. You can either do 2 pi in parentheses on the bottom. You can do it that way. Or you can do 3.89 divided by 2 divided by pi equals. That's my preferred method, is that one there. But either way, you get 0.619. I didn't multiply by 100 times 100. 61.9%. 61.9% of a circle. All right. There's your first problem on rotational motion equations. Okay, if you need to go back and rewatch that, please do so. I'm going to keep going on to number 2. All right, number 2. We have a slinger whirls a sling above their head, starting with a rotation that takes 0.42 seconds to complete one period. They then accelerate the sling's rotation for 0.31 seconds before releasing the stone. Just before they release the sling, it rotates with the period of 0.02 seconds. What was the, and this problem should ask, angular, what was the angular acceleration of the sling during the windup? Okay, first of all, I have to ask angular acceleration here because what's our unknown? What are we looking for? With angular acceleration, that one we're looking for alpha. We're looking for fishy. What does that equal? If I just said what was the acceleration if I didn't include that, acceleration is just A. However, angular acceleration is alpha. So that would be asking a different question. Now, next class, the class that follows where we did these class problems, you do look at how do you translate between A and alpha and how do you mathematically find one from the other. But right now, we're keeping them separate. Okay, so what was the angular acceleration? That means fishy equals 0. Okay, now we just have to go with givens. Okay, well, what numbers are we given here? Okay, we start with a rotation that takes 0.42 seconds to complete one period. Well, what does that equal? What does that equal? Is that our time? Because it's 0.42 seconds? Well, no, it's not. It's to complete one period, which means it takes 0.42 seconds to go around the circle once. That took 0.42 seconds, which what that really means is period equals 0.42 seconds. However, this is what they start with. So that means T initial, T naught, our initial period is 0.42 seconds. But that's not one of our motion equation variables, right? We need to figure out which one of these it is. It's got to be one of our rotational motion equation variables. So we need theta, omega, alpha, or time. Well, what is, if we go back to, I'll just do a slight aside over here, and I'll do this in, brown, why not? I'll do a slight aside. What is the definition of velocity? Well, velocity is distance over time. If we want to look at then angular velocity, let's say what's the angular velocity would be delta theta over time. But if it goes around one circle, so for one circle, how would we find angular velocity? Well, to go around one circle, this thing goes 2 pi radians. And how long did it take to do it? Well, it's the period. So from that, we get this relationship that omega, and I'll erase this one circle because that's implied within 2 pi radians. It's one circle. And then t, that's the period. That's the time to go around once. So we get this relationship here that omega is equal to 2 pi over the period. And that's just our angular velocity. Well, what's kind of cool is that AP kind of has already given that to us. It's just been hiding this whole time. It's been hiding this whole time. You've used, in simple harmonic motion, you've used period is equal to 1 over frequency. But now we get to use this middle part, right? It tells you that period is equal to 2 pi over omega. If we multiply by omega and divide by period, we would get this relationship here that omega is equal to 2 pi over period. So I give you this for my equation sheet. AP gives you this on AP's equation sheet. You get, well, sorry, they give you this. But you have to be able to convert that from here to know that, okay, anytime I'm given period, this really means I'm given angular velocity. So what this means is that angular velocity initial, right, because it's our initial period, is equal to 2 pi over that initial period. So over, this case, 0.42, right, because that's in 2 pi radians, and it takes it 0.42 seconds. This gives us that our initial angular velocity is 2 pi over 0.42. So we get 14.95, or that's rounds up to 15.0 radians per second. Okay, so there's our given. That's our given now. All right. So then, what's next? What's next? They then accelerate the sling's rotation for 0.31 seconds before releasing the stone. Okay, 0.31 seconds is how long it takes them to accelerate it. So it starts slow, and then it's going faster. But it takes 0.31 seconds to complete that acceleration. That is our time, 0.31 seconds. Okay, just before they release the sling, it rotates with a period of 0.02 seconds. What that means now, okay, that's our period right before they release it. So that's our period after this acceleration has taken place, which means that's our final period. So that's T final. That's T final, capital T, final. All right, but remember, anytime you're given a period, what are you really given? You're really given an angular velocity. Final period corresponds with angular velocity final, so omega final, 2 pi, right? So the angular displacement of one circle over the time it takes for one circle is equal to, and if we do this, 2 pi over 0.02 gives us 314. 314, this is omega final. Remember, angular velocity radians per second. Okay, so there's our three givens. All right. We now have our givens. We have our unknown. We just need our equation now. So alpha, omega naught, T, omega final. Anything over here? There's a lot going on over here. I'm going to do just erase some of these things because there's just a lot going on. I'll erase this unit circle. It's not doing too much for us anyway. Okay, but we have omega final, omega naught, alpha, and time. Well, that's what we need. Omega naught, omega final, alpha, and time. So if we take a look at that motion equation, that was, right, omega final equals omega naught plus alpha time. Okay, now all we have to do, substitute. Okay, so omega final, 314. Omega naught, 15 plus alpha is what we're looking for, time, 0.31. Okay, we'll subtract 15 over, so minus 15 to both sides. 299 equals 0.31 alpha. Okay, divide everything by 0.31. This will give us alpha is equal to, all right, 299 over 0.31. 965. 965 what? Well, it's alpha radians per second squared. All right, acceleration, but it's angular acceleration, so we need radians instead of meters. There's our angular acceleration. All right. Now I know we haven't done a ton of these problems yet. You'll do a lot of them. Just to know, as far as like, is that reasonable? Is that large number? Is that a small number? This is a large number for angular acceleration. This thing is winding up very, very, very quickly, which is kind of neat. These are real numbers, by the way. I did my research on writing this problem. These are real numbers, and ancient slingers were incredibly good at rotating these rocks really fast to be really dangerous, and they were really accurate from long range too, which is kind of awesome. Okay, but that's problem 2. One more problem for you. We just have problem 3. We have spinning roller coaster holding people against the walls. Um, by the way, this roller coaster, kind of the premise on this, I don't think there's one in Colorado anywhere. At least I haven't seen one. But premise is you have people, and that's kind of like the floor. You have people standing along the sides, and these people standing along the sides, they're here. And then it starts spinning round and round. So it starts spinning all the way around. And then what happens is the floor actually drops out. So the floor drops out from underneath you, but because of the friction between your back and the wall, you stay up. So you're moving in a circle as this entire ride is rotating, and you stay up because of the friction between you and your back, which is kind of fun because the floor just drops out from underneath you. But the faster you go, the greater your normal force is toward the center, which means you have a greater friction. Okay, anyway, that's just kind of the premise of this question. But let's take a look at this now. All right, halfway through the ride, it has an angular velocity of 5.2 radians per second. It then accelerates at a rate of 0.84 radians per second squared until it has a period of 0.73 seconds. What was the angular displacement during this spin? You can kind of ignore this 2 ways to do this. We'll only look at one. Okay, I underlined all the numbers as we got through them. So we have an angular velocity of 5.2 radians per second halfway through the ride. Now we know angular velocity is omega, right? But is this omega initial or omega final? Well, it's halfway through the ride, so that doesn't help us too much. The question becomes, does the interesting stuff happen after this 5.2 radians per second or before the 5.2 radians per second? Because if the interesting things happen after, then we'll look at it as initial. If they happen before, we'll look at it as final. Well, I say it's moving here and then accelerates. So that means this is before the interesting stuff happens. So that'll be omega initial will be this 5.2 radians per second. Okay, then accelerates at a rate of 0.84 radians per second squared. Well, we see this per second squared, and we know that's got to be fishy, alpha. Okay, so 0.84 radians per second squared until it has a period. Okay, until, that means this is now the final. So final period of 0.73. Well, remember, anytime we're given period, we are really given omega because it's just 2 pi over the period. Okay, so we have 2 pi over, and this final period is 0.73 seconds. So what is omega final really? 2 pi over 0.73, 8.61. 8.61. And this is an omega. This is angular velocity, so radians per second. All right, 1, 2, 3. There's our 3 givens. Now we just need our unknown. What was the angular displacement? You'll notice I put a little question mark here. That's how I'd kind of denote this unknown. Angular displacement, remember delta theta. Okay. So we now have our givens and our unknown. So omega naught, alpha, omega final, delta theta. We just need to find a motion equation that looks like, or that has those 4. So we need, what was it? Omega initial, omega final. This might be out of order. Alpha, delta theta. Those are the 4 that we need. Okay, do we have one that has those? Well, this one has time involved. This one also has time involved. So we aren't given one. But remember that these are just mirror images of our linear motion equations. We have this orange one here, but what does that orange one translate to? Well, V final is omega final, so we get omega final squared minus V initial translates to omega initial squared, and then equals 2A translates to alpha, D translates to delta theta. Here's your fun fact. That is an equation. That is exactly a motion equation for rotational motion. Okay, but here's the thing. I don't give that to you because AP does not give that one to you. I don't really know why they give you the others, but they don't give you this one. No idea. But this one is just as important, just as valid. So you have to know that you can get this equation from the linear motion equation that looks basically the same. So right now, on your workbook, write this equation down on your equation sheet. Write it down because I want you to remember that you can use it. And then come AP test time or even our unit test, just know that you are not given that equation. So you have to be able to come up with it from this one over here. Okay. So we've got, oh, I just need the next page here. All right. We've got now this equation that we've just come up with, omega final squared minus omega naught squared equals 2 alpha delta theta. All right. All we have to do is plug stuff in now. Well, omega final 8.61 squared. Omega initial 5.2 squared is equal to 2 times alpha 0.84 times, sorry, my little drawing of this roller coaster kind of got in the way. 2 times alpha, which was 0.84, times delta. Theta is our unknown. Okay. So then, if we bring this into our calculator, 8.61 squared minus 5.2 squared. All right, so there's our left side, 47.1. 47.1 is equal to 2 times 0.84, 0.84. We get 1.68, 0.68 times delta theta. All right, so then divide both sides by 1.68. So 47.1 over 1.68. Here we go, 28.0. Delta theta equals 28.0 units, radians. All right. Nice. There we go. One last part. All right, how many circles did it complete during this acceleration? All right, what are we doing here? Well, we're going from radians to circles. Really, all that means we're doing a unit conversion, right? Unit conversions, we use train tracks, 28.0 radians, these train tracks, right? Immediately we take this unit, drop it down because we have to get rid of it. And what's awesome is I have finally realized within about a week of making this video, finally realized the best way to do this. Stack things that are equal. Well, we have radians and we want to get to circles. We decided on the first or on the page earlier, right? Remember your unit circle. One circle, I guess I should make that circle. One circle is equal to 2 pi radians. All right, so stack things that are equal. One circle equals 2 pi radians. Okay, radians top and bottom, they cancel. We're just left with circles. So how many circles do we have left? 28 over 2 pi. 28 over 2 pi. Oh, I did it. I did it myself. 28 over 2 pi, right? That gave us 28 over 2 times pi. So over 2 over pi. There we go. 4.46 circles. 4.46 circles is how many circles it completed. All right. Well, that just about does it for our video here on rotational motion equations. This is meant to go with assignment 7.01 from your workbook. So there's our class problems. 7.01 starts off with, right, these express the following angles from degrees to radians, because you need to know how to solve for radians. A couple of practice problems here. It's just front side, back side, all in these things. Be careful about units all over the place, as opposed to minutes and seconds, right? Radians is what we need, and seconds is what we need. All right. If you have any questions, please do let me know. Otherwise, that'll do it for this video. Have a great rest of your day, and I'll see you next time in class.